Why does radioactive decay occur at all? Why would a uranium nucleus that has been sitting happily in the ground for 4 billion years suddenly decide to spit out an alpha particle? And why is it statistical? Why is, if you have 2 uranium nuclei, there's a chance one would decay at a certain amount of time and one wouldn't. They don't go bad. It's not like a milk expiration date. So why does some uranium decay before the half-life, some decay after, and why decay at all? Well, the model that's used is the idea is that there's a potential barrier holding the alpha particle in a uranium nucleus or a heavy nucleus. So there are 2 forces that we need to talk about. One you're familiar with, the repulsive Coulomb force, right? Imagine you have a big uranium nucleus containing protons and neutrons, so it's positively charged. And part of that uranium nucleus, there's a little alpha particle in there bouncing around, which is also positively charged. They hate each other. Positive charges dislike one another. So if the little alpha particle, let's draw it as a little alpha, if the little alpha particle can get out here far, this is a plot of radius or distance from the center of the uranium nucleus, if it can get far enough away, the repulsive Coulomb force, like charges repel, will push it out. Great, but why is it stuck there in the first place? Well, Coulomb forces are actually weaker than another type of force in the nucleus called the nuclear strong force. The nuclear strong force is a force that attracts protons and neutrons together. So, neutrons, think of it as the glue holding a nucleus together. That's why you can't have a nucleus of just protons. I'm not sure if you've ever thought of that, right? There are no isotopes where it's just 2 protons stuck together. There is no helium-2. You have to have at least 1 neutron in there for those protons to behave. Now, let's expand on that for just a bit. So as you get more and more protons in the nucleus, you need more and more neutrons to hold that together. Eventually, the nucleus gets so big, you have so many protons, that you need not just a 1-to-1 proton to neutron ratio, you need even more neutrons than protons to hold the nucleus together. And larger nuclei can be very unstable. So here's a plot showing here the atomic number, which is the number of protons, as a function of the neutron number, which is the number of neutrons. And you can see that only low mass, low atomic number isotopes or elements have a 1-to-1 ratio. For example, helium, you can have 2 protons and 2 neutrons. Carbon, you can have 6 protons, 6 neutrons. Oxygen, you can have 8 protons, 8 neutrons. Neon, you have 10 protons and 10 neutrons, and so on. As you move up the periodic table, that's not the case anymore. Uranium-235 has 92 protons, and then 235 minus 92, which I'm going to totally do the math wrong in my head, so I won't even bother, 140 something neutrons present, right? So you have a lot more of the glue to hang those protons together. The nuclear strong force is stronger than the Coulomb force, but it works over a much, much smaller distance. So if you're very, very, very close to the center of the uranium nucleus, the alpha particle is stuck in what we call a potential well. Imagine it like a roller coaster. If you don't have enough energy to get over that first hill, you're constantly going back and forth, trying to get over that hill, but unable to. So think of it like the alpha particle is trapped in this little, inside the uranium nucleus, bouncing around, bouncing off, hitting this potential wall again and again and again and again and again. Millions or billions of times a second. Smashing into the wall and bouncing off, smashing into the wall and bouncing off. Over and over and over. In classical physics, this would never resolve itself, right? The alpha particle would always be trapped. because it will never have the energy necessary to overcome this potential barrier. The roller coaster, if you will, doesn't magically gain energy. If you're going back and forth, it'll be stuck forever. But this is not classical physics. This is quantum mechanics, quantum physics. So we talked about Heisenberg's uncertainty principle and how when you measure the presence of a particle, sometimes that particle's location can be a little uncertain. So after hitting this trillions and trillions and trillions of times, the alpha particle can tunnel through and magically find itself on the outside of this barrier. There's a very small probability of this happening, a very, very small probability. But if that alpha particle is trying it trillions and trillions and trillions of times, eventually it will escape. So that's where the statistical nature comes in of radioactive decay. You don't know on what attempt that alpha particle will be successful. You just know that after some time it will eventually be successful. This alpha particle, once it tunnels across this potential barrier, now it's far enough away that the repulsive Coulomb force takes over and the alpha particle flies off and you have a radioactive decay. Uranium is no longer uranium because you've lost 2 protons and 2 neutrons. This model helps explain radioactive decay and the statistical nature of it. Some isotopes have smaller potential barriers than others. So uranium-235 and uranium-238 have slightly different potential barriers, so they have slightly different probabilities of tunneling through, which means they have different half-lives. You can also use this model to explain nuclear fusion. So rather than using alpha particles, let's look at 2 protons bouncing together. So here's the potential, same curve, for a single proton sitting in space. And I try to slam another proton into it. When I try to slam another proton, most likely that proton will approach, feel the Coulomb repulsive force, and then fly away. So 2 protons, like charges, repel. They hate one another. I have to keep on slamming that proton into the other proton. Now there are 2 ways I can do it. I can either slam it with a high enough energy that I overcome the potential barrier and there's no barrier at all for me to create a helium nucleus, or actually proton to a proton would create deuterium or helium-2. Sorry, hydrogen-2. But at the temperatures in the sun, about 15 million Kelvin, 15 times 10 to the 6 million, 15 times 10 to the 6 Kelvin, 15 million Kelvin, protons don't have enough kinetic energy to overcome the barrier. But there's so many protons in the core of the sun, smashing into so many other protons, that the proton can tunnel through, has a probability of tunneling through, and when it tunnels through, now it's trapped with that other proton, giving us deuterium. So now I've just created heavy hydrogen, right? Hydrogen with a neutron. And then a positron and a neutrino would pop out. So this barrier tunneling works with particles, because remember, we think of these like little pieces, like little BBs, like little cells or physical objects, little balls, but they're not. This acts as a particle and a wave. So it can tunnel through these potential barriers. It's kind of like if you would walk into a door, or if you've ever seen a fly in a window, hit the window as it's trying to fly out. A fly's dumb, or a moth is dumb, it doesn't know there's a window there. It repeatedly hits it trying to go out. In the quantum world, if it hit it enough, eventually, probabilistically, it would tunnel through and find itself outside. That doesn't work on the classical world that we live in, but in the very, very small quantum realm, it's possible. So this is the concept of tunneling.